I will start by introducing Schaffner to those who doesn't know Schaffner, and then I will pass it over to Abir to present some technical aspects and our products, of course. So maybe first, let me introduce myself. I'm the sales manager for Schaffner for France, Belgium, and North Africa. I've been working for Schaffner for 20 years, and so I have a background of EMC engineer. So. Not this one?
Hold on a second. Yes. Yeah.
It works. Okay. Thank you. So just a short overview of Schaffner. We are the world leader in the EMC filtering. Let's say that it's true for Europe, and for the world, it's hard to say, to be frank. We are addressing growing market with a harmonics filter, solution for electromobility and magnetic components. Our headquarters is based in Lutherbach. It's a company that was founded in 1962, and we are, let's say, 3,000 people in the world, mostly in the factories in Asia. And we are listed at the Zurich Stock Exchange since 1998 for a turnover of 170 million euro over the previous fiscal year, because we are just ended the fiscal year end of September, so we are in a blackout period. The footprint. So originally, Schaffner started everything in Switzerland. As I said, the headquarters is in Switzerland, and everything started in Europe. We are well represented in Europe with sales offices in the main countries. Let's say we have the headquarters in Switzerland, and we also have our logistic center. Our bigger logistics center in France, in the Alsace region. We also have a sales unit and warehouse in USA, in Edison near New York, and our factories now are only in Asia, in Shanghai and Thailand. We used to have a factory in Europe, in Hungary. And we sold one of our division, which was the power magnetics division, and we sold the factory as well. At the beginning, we thought that it could be complicated with all what's happening in the world and the transportation and so on. But finally, with the energy costs that increase dramatically in Europe, we don't have the same problem in Asia. So it's surprising, but well, not that surprising, but at least we could maintain our costs in Asia, what some of our competitors could not do in Europe. To counterbalance the only production in Asia, we use our main hub in Wittelsheim in Alsace in France, where we actually stock a lot of products, standard products. So we heard about lead times. We can also tell that we have quite good lead times compared to competitors. When some competitors have announced 52 weeks, not to say 1 year, we can offer for the same product 14 to 16 weeks without any problem. No. And we just changed our logo. which is now more power to you. So it's very new, very new. As I said, we had a power magnetics division. Now we divest it and we will focus on our core business, which is EMC. So we have now two divisions. It's automotive division and industry division. We represent, Abir and myself, the industry division. So we will not talk about automotive product at all. We heard about Premo in another presentation, so we will not talk about this kind of product. We focus now on our core business, which is EMC, so electromagnetic compatibility. And what we want to say with more power to you is more power to our customers. Just to mention that we are willing to offer solutions instead of products. So we want to let our customers working on their products, on their innovation. And we will accompany them with EMC pre-compliance services, with customized solutions, and of course, using our products on the shelves, adapting them, and so on. So now we'll pass it over. Abir.
Thank you. Well, hello everyone. Allow me first to introduce myself. So I am the FAE, the Field Application Engineer for Schaffner, covering both France and Belgium. And through this presentation, I would like to answer a few questions that we might all face when we tackle the EMC issue during the development of a product. So first of all, why is it so important to take into account? Then we will see the purpose of implementing an EMI filter, how to install it, and which one to pick, because this can be very tricky. And after that, I will present to you a few filters that are dedicated to some specific applications. So as my colleagues mentioned earlier, it is very important to take into account EMC since the very beginning of the design of the products, because first of all, this will allow you to use multiple techniques that are not expensive and easy to implement. And otherwise, if you discover this, I don't know, is the sound okay? Because, okay, sorry. I'm not used to hearing myself, so it's a bit weird. If we discover all the EMC issues at the end of the validation, it could be very expensive and it could be very stressful as well. I think everyone who has been through certification knows that. And another purpose that is very important is the certification part. So if you are going through an EC marking, CB certification, or a UL certification, you will definitely face the EMC directive and all the standards that refer to it. And the core of all this is actually to ensure the compatibility between the system and its environment. Because we can have, for example, a lighting system, and it depends on the environment in which we install the lighting system. For example, if you install it in an operating room in a hospital, in a railway system, or within a commercial accommodation, you will definitely have different EMC requirements. Sorry. So when it comes to EMC problem modeling, the most common model is actually the source and victim model. I think we are more or less familiar with that. So we will have two types of coupling: the conductive coupling through the cables and the radiative coupling through the waves that are emitted by the system. And this also leads to inductive and capacitive coupling. So the inductive one is known when we have a current that is going through a cable next to a loop. So we create a magnetic field, and after that we get a common mode current that is spreading throughout all the system, which can be more or less hard to filter. The capacitive coupling is a bit different. It's when we create parasitic capacitance between two conductive surfaces, and after that we due either to bad earthing or to some filtering dimension issue, we can have this kind of filtering. So a little reminder about the common mode and the differential mode currents. So this is the most known one. This is what we have at 50 Hertz. It's the differential mode current that we can see between the line and the neutral, for example, in a system. And besides to that, we have also the common mode current. And we usually say that the current takes the shortest path to Earth, but actually it takes the path that has the lowest impedance. So in lower frequencies, the differential mode is more present because the closest path to Earth is usually through the neutral. But when it comes to higher frequencies, the most present one is actually the common mode, and the filter should cover both. So these are some standards that we can find, some limits that we should respect when it comes to standards. And as I said earlier, they depend both on the product type, but they mainly depend on the environment in which we put the filter. And filtering must cover, for most civil applications, the range of conducted emission, which is between 150 kilohertz and 30 megahertz. So this is applicable for most of civil applications. And for other frequency regions, we have either other standards that apply, such as radiated emissions, or we have also some other standards for the harmonics. So if you have gone to a testing lab and watched some conducted emission test, you must have heard of the LISN, the line impedance stabilization network. So we usually, when we do the test, we have our equipment on the test. We have our EMI receiver or EMI spectrum analyzer. And between the network and the system, we use the power supply of the LISN. The idea behind this is to disconnect completely and separate in high frequency, in the frequency range of conducted emission, the network from the product, so that we can only see the measurements of the conducted emission of our own equipment. And these are some examples of what we can measure through and with and without filter. So the first one is for a mechanical ventilation system with double airflow. So the measurement that you have on your left is the one without filter. And as you can see, we inserted the filter within just upstream the inverter, and we could get rid of all the noise. And this is another example as well. So this is for a machine for food industry, mainly for bacteria growth, I think, to do some tests. And you can see the equipment under test and the LISN in this example, and we can see clearly the effect of the filter. So as you could see downstairs, mainly we have a multiple choice when it comes to selecting a filter. So you can either use a chassis filter, you can use filters that have IEC inlets, we can use a filter on PCB. There are multiple choices of like a large panel, and we always wonder which one should I pick and which are the criteria that I should use in order to choose my filter. But before that, so just if you need any details about the data sheet, about the 3D drawings of the filters, you can just find them on our website. So before answering that question, I would like first to tackle another problem that is as even more important, I would say, is to how install the filter. Because from my own experience at least, I can tell that 80% of the problems that we see are actually cabling problems. They are even not problems about the filter itself or about dimensioning the filter. It's about the cabling itself. So I would like to give you some hints about the cabling and to make sure that, that you pick up the right filter. So the first thing is to keep the cables as short as possible. There is no need to have loops or to have like long cables, because in this case you will create a lot of antennas within your system, either magnetic or electric antennas. After that, just use this, do not use the scheme that you have at your left. Do not mix the input and the output cable within the cabinet, for example, because this is an example that we have had, and we moved from a non-compliant system to a compliant system. As you can see, it's around, I think, 200 kilohertz, because actually when the cables, the input and output cables were all together, there was simply a crosstalk between these cables, and they find, I mean, the filtered signal was going right to next to the unfiltered signal, and at the end of the day, the filter was completely useless. So in this typical example, no matter what kind of filter we put, it was not useful at all. Okay. Another example is the saturation. The saturation is not due to the installation issue, it's mainly due to the filter dimensioning. So this is a vacuum pump that we have tested, and we just picked up a catalog filter, and actually we picked up more than one. So, and during all tests, we had a high noise at 100 kilohertz, and we could never get rid of that noise. And it was simply due to the geometry of the common mode choke within the filter. It wasn't the right dimension. It wasn't enough to get rid of the noise. So what we could do is that we modified the capacitors within the filter in order to enhance the performance of the common mode choke and enhance the performance of the filter in general. So the idea is that we can use filters from the catalog. We have like some simple parameters that we can use to select the filters. Otherwise, we can simply modify filters that are within the catalog. And at this stage, we don't even mention customized filters. We can simply change the capacitor value and still keep all the certifications of the filter and handle it internally as a catalog product. Another criteria that is important when it comes to filter selection is the leakage current. The leakage current is actually what we face. I don't know if you have faced this or heard of it, but whenever we install a filtered equipment or an external filter in an installation, we get a claim about the differential circuit breaker, that it trips. And usually this is due to the common mode capacitors, because filters, this is a typical scheme of a filter, they help us filter a high frequency signal, but through the common mode capacitors that we have between each line and earth, we generate a leakage current that is proportional. At the end of the day, it is proportional to the common mode capacitor. So how do we get a balance between the leakage current that we should keep very low and the high value of the common mode capacitor that we should insert within the filter? So that leads us to a specific application, and that has a very specific requirements. It's actually the medical standard. So if you have ever faced a medical standard, we all know that it has a very severe requirement when it comes to leakage current. So we are simply not allowed to put any any common mode, any common mode capacitors within the filters. So to answer this requirement and to be able to meet it, Schaffner has a solution. It is the filters with a B version. So all the filters that have a B version, also, yes. All the filters that have a B version actually can comply with the medical requirement. Like it's mainly all of our chassis filters, but also all of our filters with the IEC inlet. And unfortunately, if we respect this requirement, we definitely affect the performance of the filter. So here we have the same filter with and without the common mode capacitors. And as you can see, we severely impact the performance of the filter. This is the filter attenuation. So we severely impact it by removing the capacitors. So in order to solve this issue, what we can do is to add an earth choke to our filter. So there are a lot of filters that we have. They definitely don't have common mode capacitors to be able to comply to the medical standard, but they have an earth choke, and this is how we can enhance the filter performance without impacting the leakage current. And another aspect that is important in the medical standard is the means of protection. So whenever we have a requirement about a 2 MOPP component when it comes to patient-coupled device, so if you have a medical device that is related directly to the patient, you need to have a class 2 isolation. This is a double isolation. And in order to respect this, we have filters that already include this kind of IEC inlet. So this is the FN2274 filters. These are available downstairs if you want to check them. We also have other filters that meet the requirement of only a class 1 isolation, such as these filters. So we have the FN2092 series with multiple versions depending on the performance. These are only with the IEC inlet. We also have the same thing, but with a fuse holder or a switch. So these would be the 9260 up to the 9264. They don't have any Y caps. They can have an earth choke, and they have fuse holders. So these would be interesting for medical applications mainly, or for any other applications they can be suitable as well. You have, if you are interested into a filter that integrates both fuse holder and a switch, you can use either a single stage FN9280 or a double stage FN9290 IEC inlet filter. And in order to complete this, we also can afford the lock retention cables that go all the way with these filters. These can also meet some requirements in terms of either medical or some other standards in terms of electrical security. So this is the first example for filtering selection. So it would be the leakage problem issue. Based on the same thing, we can have another example for the DC fast EV charging systems that we have. So it's very similar to the medical standard. The standard for the DC chargers has a specific requirement in terms of common mode capacitors. Their value should not exceed 1 microfarad for the DC output. So this would lead us to design our filter accordingly. And to meet this requirement, we have different solutions for DC filters. But before that, just to go quickly through the architecture of the DC fast chargers. So these are the EV chargers that have an integrated converter. So we have first of all, usually the three-phase AC filter. This is the filter to disconnect the system from the network. After that, we have our LC or LCL filter in order to filter the signal. Then we have either the converter or the parallel power modules, and at the DC output we can have at the DC output we can have the DC filter, and at this level we need to respect the requirement of 1 microfarad of common mode capacitors, which can be a bit limiting in terms of filtering. That's why we have developed these new filters, the FN2220, the FN2230, and the FN2240. So these filters can go from 150 amps up to 600 amps, and they are available both for either 1000 volts DC or 500 volts DC. And the advantage of this filter that the common mode capacitors can be really adjusted according to the performance that is required. Well, that would be it for DC charging. We are now taking another example, which is the lighting applications. So the specific thing about the lighting applications, especially the LED applications, is that they are using and referring to different standards in terms of EMC, and that the limits and the frequency range are different. Actually, in terms of frequency range, we don't start at 150 kilohertz, but we start at 9 kilohertz. So that is a lower frequency, which make the differential mode problems more present. So in order to filter this kind of frequency range, we need to have a filter with the differential chokes. We don't use only common mode chokes, but we use also differential mode chokes. So we have specific filters that are dedicated to lighting systems, such as the FN2560 and the FN2580. So these filters have either 1 or 2 differential mode choke at each line, and as we can see, they can be really helpful. Sorry, they can be really helpful with the emissions when it comes to differential mode, especially in lower frequency. We can see the impact in the measurements that has been performed on a system, including these filters. And when it comes to LED system, we all know that sometimes there is just no place for a DC, for a whole filter. That's why we have a component. It's the ED100 or ED101 common mode choke. So this common mode choke has the advantage to have a high value of stray inductance, which makes it a very efficient differential mode choke as well, just by construction, which can be really helpful because on a PCB it can replace both a common mode and a differential mode choke. So this is typically advised for LED drivers. Well, that would be all for the applications, I guess. And yeah, we can move to your questions.
Okay. Thank you, Abir and Sylvain, to get to know your company, products and service portfolio. Are there any questions for Abir or Sylvain?
For the lighting application, is it imperative that you use differential mode chokes? Not you just use only capacitors?
Yeah, it's possible to use differential capacitors, but the problem of the capacitors that they will be increasing the power factor. So we need, in order to respect this requirement for harmonics, because they have also another specific requirement when it comes to harmonics, we prefer to use differential mode chokes.
We'll give the mic, Mart. It's for the recording. It's important. Joost's question is not recorded, but
Mute the recording. No, I have a question with respect to the filters, because let's say most of the electronics nowadays are PWM. Yeah. When it comes to testing of the filters, it's commonly done at 50 hertz or 60 hertz, dependent upon the country where you are available. So that applies that your withstand capabilities can be up to 1,000 volts or 1,500 volts or 2,500 volts, 50 hertz. But what about 20 kilohertz, 50 kilohertz? How does it go with the Tangens delta, i.e. the losses of your Y capacitors and X capacitors? How is that regulated?
Not sure to get your
Yeah.
question.
Yeah.
Yeah.
Are they blown out? Yeah, just as soon as you have high frequencies involved across the components.
When you talk about PWM, it's on the motor side or on the load side.
Yeah, if you have a bidirectional inverter, then of course it's at both sides.
So yeah, if it's a regen application, yeah, it's both sides. But in this case, you must have an LCL filter to filter and to smooth actually the current.
Yeah.
And then you have the EMI filter. And if you don't have the LCL filter, then you can have some serious problem with the EMI filter.
Okay.
Yeah.
Then another question: is it in the line IE portfolio of Schaffner also to have active filtering?
We have.
We have.
Yeah, we have.
It's not mentioned.
Yeah, we have. We did not mention it, but we have. Yeah.
Okay.
Yeah. Okay. We have. They are rackable. We have the 50 amps compensation active harmonic filter for harmonics, for low frequency harmonics. Huh?
Yeah, for the three-phase system or for
Yeah, three phase. Yeah, 3 phase and 3 phase plus neutral. Yeah, 3 wires or 4 wires.
Yeah, not for the leakage current compensation.
Not yet, but it's in the R&D side.
Okay, but these are harmonics, like.
For the active filter that we have at the moment, it's purely harmonics, low frequency harmonics. But for leakage current compensation, it's on R&D side. Cannot say too much.
okay, yeah. For the recording, that's my boss over there. Okay. Are there any other questions? Yes.
You talked about capacitors to connect to the ground, to also comply with the medical specifications. However, in hospitals, mainly there is an IT grid. So meaning that you exclude these capacitors towards the ground.
No.
Right?
No. You exclude the discharge resistor because it will make trip the impedance controller. So that's the resistor that you will get rid of. The capacitor can remain, but it has to be quite low. It has to be low.
Yeah. The switch which is on your filters for IT grid and TNT grid.
We propose it only on a customized solution, this kind of switch.
Okay. Yeah, because this one disconnects the capacitors.
Yes, right? Yes, yeah. But for special purpose, not only for IT grid. Not only for IT grid, for special purpose when low leakage current are requested.
Yeah. But how then can you still comply with the EMC standard without these capacitors?
Well, if it's an IT grid, it's not mandatory to be compliant with EMC. So it's only the purpose of having a filter on an IT grid. It's only to prevent your equipment to be disturbed, in fact. So, but actually, you're right. If you disconnect the capacitor to the ground, the attenuation will be much worse. Yeah, yeah, for sure.
Okay. Any other questions in the audience? Well, then thanks you a lot,
Yeah.
Sylvain.
And thank you, Tom, also for the invitation.
Thank you.
It was a rather short notice because we start only to work with TeleRx. So it's really the beginning. We don't have years and years of partnership.
Flexibility.
Yeah.
Thank you.
Thank you.